what we're going to do here is we're going to do a couple little experiments. You probably already know the answer what x to the 0 power means, but we're going to prove it. We're going to prove it still using the table, and we're going to prove it using what we know about what we just did in our warm-up with exponents on number 2. I need you and your partner to complete 1, 2, and 3. There's not a spot on this for your notes. You can choose to do it above the Are You Ready portion or do it in your math notebook. Let's look at this and try not to hurt brains. What I'm going to look at is the pattern in the table. So who noticed what's happening to our outputs? 81 to 27. 27 to 9. Yeah, is everybody seeing that divide by 3? Okay, so 9 divided by 3 is 3, and 3 divided by 3 is 1. This is it. What this says is 3 to the 0 power is 1. So right here, we just proved why the 0 power pumps out an answer of 1. Now let's look down here. We looked at the warm-up. What did we do with our exponents when it was multiplied like that? We added them. So 7 plus what would give us 7? 0. So that means that question mark needs to be 0. And here's what that means. Something times 9 to the 7th needs to equal 9 to the 7th. So 9 to the 0 has to equal 1. All right? Down here, we subtracted, right? So what would that number need to be? 12 minus 0 is 12. That number needs to be 0. And here's what's up. If I got 9 to the 12th over something and it equals 9 to the 12th, what does that something have to be? 1. Which again shows us anything to the 0 power is what? 1. So what's 5 to the 0? 1. What's 2 to the 0? 1. What's pi to 0? 1. Everything to the 0 power is 1. No, I don't think there is a 0 to the 0 power.
What's 1 to 0?
I think, let's try. I think it's going to give me undefined. I've never done this. Thanks for 0 to the 0 power. Domain error.
What about 1 to 0?
You can do 0 to the 1.
Realistically, it'd be 0 though.
Well, no, because 0 to the 1 is 0. Everything's 0. Usually 0 power is 1. That's why I thought it'd give us an error. 1 to the 0 is 1. And I showed kids another way to prove, because I get that people think it's 0 sometimes. Here's the other way I showed to kind of prove it. I use 2's. So 2 cubes, 8. 2 squared is 4. 2 to the first is 2. 2 to the 0 then has to be 1. Divided by 2, divided by 2. But check this out. None of my answers change if I multiply by 1. So again, like 1 times what is 1? 1. All right, so that's the other proof. 2 to the 0 has to be 1. I get the reason it's in here like this is because we get that it looks funky. Okay. Here's what we're going to do now. We're going to look at bacteria in a lab. And in this lab, we're starting with 500 bacteria. They reproduce by splitting, binary fission for my science heads. And on the hour, every hour they split, and there's double as many. I need you to finish the table for a bacteria. Be mindful right here. I was tempted to make a little mistake. Be mindful right there. Then focus. Here's where we're really going to focus. Writing an expression and an equation to model our situation. All right? So get after this with your partner. 1 ABC. This is in your printed notes.
Oh, they are jorts.
All right, y'all. Let's take a look. After 1 hour, how many bacteria do I have? After 2 hours. 3 hours. 6 hours. 32,000. So, who's got an expression that I'd like to throw out there? Even if you're not 100%, it's cool. We're going to use it. What do you think, Will Baker?
Y equals 500 to the power of x plus 1.
So, to the power of the previous years plus... Okay, so where's the doubling happening in your expression?
Well, it's y equals 500 to the power of x plus 1.
Okay, but where's the doubling happening?
It's the x plus 1.
Okay, so if I have 500 to an exponent, let's say it's 2.
Oh, no.
Okay, no, that's good. No, that's awesome. Thanks, Will, for pointing that out.
I was just trying...
Hadley.
I did that wrong.
That's great.
500 times 2 to the power of 2.
So you're telling me, Hadley, that I'm doubling 500 a certain number of times? Okay. Everybody seeing why this is the function? I have 500. I'm multiplying by 2. The number of times I multiply by 2 depends on the number of hours, correct? So our expression is that right there. 500 times 2 to the t power. Which means our equation, very nuanced, the number of bacteria equals 500 times 2 to the number of hours. And then C, 0 time, without even looking at a function, 0 times should be how much bacteria? We got it right here. 0 time, we should have what, Bob? 500. So let's test that out. If I have 500 times 2 to the 0, what's 2 to the 0? 1. 500 times 1 is?
500.
Guess what the number one wrong answer here is?
0.
1. Do I multiply first or raise to my power first?
Raise the power first.
But this is first, Grant.
Oh.
Power first, Grant. You're right. I'm making you question yourself.
Exponents.
Exponents first. PEMDAS is trash.
Parentheses. Exponents.
Gems. Grouping first. There's no grouping. Exponents and roots next. Exponent. Okay. If you do 500 times 2 first, you're wrong. All right? Now, in this other biology lab, they have single-cell parasites. Okay, and their growth is modeled by this function. With your partner, what does 100 mean? And what does 3 mean in context? With your partner, let's go. Who can tell me what the 100 is in context? Finn.
The starting amount of parasites that they have.
Yeah, they're starting with 100 parasites up in there. What's up with the 3? Raymer.
It triples beside doubles.
It triples now. So times 3 times 3 times 3 is what's happening over and over because of that exponent. So what you're tasked with doing next, on the other side of your notes paper, that's by the way, that number, what an a b to the x, that number that's getting raised to the power, that is called the growth factor. If it is a number that is greater than 1.
If it is greater than 1, if it's lower than 1, is it like the negative factor?
Decay. So to grow, we have to multiply by a number bigger than 1, otherwise it gets smaller. So you're going to put this to work. We're going to compare bacteria and parasites. So on the back, graph them both. This will go pretty quick. Okay, so for graph A, we're starting where? 500. We just saw that with doing the 0 exponent thing, right? After 1 hour, how much was up in there?
1,000.
1,000. 2 hours.
2,000.
3 hours.
4,000.
4 hours.
8,000. 3 is on the wrong line.
I messed it. Oh, dang. 3. I'm like zoomed way in on here.
Yep. Yes.
And then 4.
Is for 8,000.
Uh-oh.
Uh-oh.
All right. There it is. There's my bacteria. And you notice, is it a constant rate of change or is the rate of change changing?
Change.
Yeah, it's getting steeper and steeper, right? Let's check out this.
The rate of change.
Let's check out this parasite. All right, Asher. So how much is that one starting with? 100, which is right about there. And what's happening to these 100 after 1 hour? They triple, so they're like 300, right? So that's 250. So somewhere around there. Then after 2 hours, how many?
900.
So somewhere in there. After 3 hours,
2,700.
2,700. After 4 hours,
8,100.
ooh, so it's catching up. You guys seeing that? It's catching up.
It's above.
It's past it.
It caught up and passed.
4 hours.
Why is this one steeper?
Because
Because rate of change is greater than
Growth factor. So who can tell me where we see 500 over here? Micah.
y-intercept.
Yeah, when we input 0, we get 500 out. We're starting with 500. So where do I see this 100 on the right?
y-intercept.
The y-intercept or the vertical intercept, right? Where am I seeing 2 and 3?
How much factors?
Yeah, what's the fancy word we have for 2 and 3 today?
Growth factor.
Growth factor.
Where do you see it on the graph? Like,
You see it by the doubling and tripling. So you could do something, I like that he asked that. If it went from 4,000 to 8,000, if I do 8,000 divided by 4,000, that gives me my doubling thing. Over here, if I did my, let's say 100 to 300, 300 divided by 100 is my growth factor of times 3. It's there. It's just a little bit buried, but it's still there. We already did that. There's the graphs. Your lesson summary, then homework's in the top basket.